Okay. So before I start, let me just remind and announce again that tonight we have something called Pizza Night. As the name indicates, well, we will have some pizza and also some drinks, and this is just an occasion to discuss a bit more. We can just stay here after the last lecture, and the pizza should be here at 6, and we can have extra opportunity to discuss maybe in more informal atmosphere. So we hope you may stay around. And well, let me just continue. We did much work yesterday, I think more conceptual, so that today we can take some advantage of that and discuss various statements which follow from.
But I have one question.
Of course.
Do we have notion of complex conjugation classically, or
no, we can consider these two parts as independent. I mean, we can like continue them to like independent domains and think of these unbarred and barred variables as independent ones.
But I mean operators.
Also for operators.
The fields.
Well, we can think of them as independent ones. At the end, we can identify one with the complex conjugate of the other. But in principle, we can treat them as, in particular, this, we will see today, this Virasoro algebra will arise. We can think of it as two independent copies. Okay, so just to briefly remind, I presented this radial quantization procedure yesterday, and we saw that this operator product expansion plays important role. And also when there is momentum tensor plays an important role. I introduced primary fields. And my definition was how they transform under conformal transformations, but then we notice that you can also characterize them by the form of OPE with energy momentum tensor, which looks like this, and similarly with T-bar component. So these are singular terms. The other ones are non-singular in this expansion, but the singularities are important when we make these contour integrals. And this is this H here is a dimension of the operator, or wait, different names are.
And the
yes.
T is also constructed from the primary fields.
No. T is an energy momentum tensor. It is an operator in itself.
Isn't it momentum energy?
It is this remnant of an energy momentum tensor. I showed that from certain conservation laws and the tracelessness conditions, it follows that the only non-trivial component which remains is the holomorphic one, this T of Z, which is holomorphic function of Z. And the other one, T bar of Z bar, but
usually the energy momentum tensor is given by the fields of the theory.
In principle, yes. However, I am discussing it on a more, let's say, abstract level or general one. I'm not telling you yet how it is related to the fields of the theory. If you define a theory by some Lagrangian or action and so on, then you can indeed derive an energy momentum tensor. We will see that also in some example. But now I am more general, and this, in particular, this OP, this is general feature of all 2D CFTs, at least this, which I'm discussing. So whatever definition of a particular theory is, you should find this OP. And remember, I introduced this notation with radial ordering first, but in what follows, I will ignore this R and just write it. And it's important that we take this OPE. There are different notations. Sometimes people just write it like this. Well, I wrote equal, but then those dots. So this is this operator product expansion. This is important that we take this expansion where Z approaches W. And we will see in a moment that, in fact, T itself, well, this is also an operator, but this is not a primary operator. So that's also important statement. All right, so that was one issue we discussed. So, I mean, everything here is important, that these are primary fields, that we have this radial ordering, that this is the OP, and so on, and that the energy momentum tensor plays important role, and all that is in that expression. Okay, and another important result which we found was conformal word identity. Well, this was the ordering which in this radial formalism, what normally would be equal time surfaces are circles of fixed radius. So it puts operators in the order according to the distance from the origin. Okay, and we found one example of word identity which involves energy momentum tensor as well, namely also using this idea of OPE and contour integrals. So now you may recognize that similar expression, well, not exactly the same, but of similar form appeared in the lecture of Sabrina, for example. Well, so this is one reason I am presenting what I'm presenting. And then, well, this you can think of this as a sum operator acting on the correlation function which does not involve T. So you can think of this expression either as a relation which well, relates two different types of correlation functions, or a way to find this type of correlation function with extra insertion of T, just starting from simpler correlation function and using some extra operations which give you that. And there are other types of such word identities. I will not be deriving them systematically. Maybe one other example will also appear a bit later. But it's important to understand how they arise. Yeah.
Sorry, it's a bit of a late follow-up question to earlier thing. So how do I think about radial ordering when in a complexified picture, when W and W bar decouple? How should I think about radial ordering?
In which sense? How do you?
Well, so it's nice and well defined to say that ZZ bar can be compared to WW bar when Z bar and W bar are the complex conjugate of Z and W. But in the complexified picture, when W and W bar are not related by complex conjugation, how do I think about radial ordering?
Well, in fact, this T of Z, this is just holomorphic quantity depending on holomorphic Z. So what is important that Z needs to be close to W. If you would think that W bar is like independent coordinate, then in this expression, in a sense, we ignore it because here, anyway, whatever appears here is just holomorphic in well, Z and W. I mean, this derivatives and so on. They are just in
general,
W.
As two primaries, the generic independence is not necessarily holomorphic. There's no conservation law in them. How do I think about radial ordering? Like, what does that actually mean in the specified picture?
Well, one way to think would be that you, in fact, don't take them independent yet. You just think of them as W bar being W, and then indeed we have well-defined situation. You know what it means that points are close. I mean, which is which, and then you can make computations, and after you make the computation, you can continue to arbitrary W bar.
Thank you.
Okay. Well, this is just a reminder, and let me now write yet another very important example of OPE, also involving energy momentum tensor, and in fact nothing else. Namely, I'd like to take two energy momentum tensors. So to find the form of that, I mean to derive it, you can consider a sequence of two conformal transformations. And then in a way follow the logic I presented yesterday. So I will not present the whole derivation. It would also take a bit too much time here, but I will just write the result, which is the following one, and this is also a crucial thing. There are singular terms starting from such an expression. And so on. So you see that we have here a term which has singularity of higher order than quadratic, which means first of all that indeed T of Z is not a primary field. Because primary fields have this property that the most singular term is quadratic. So that's one important conclusion. Another one is that here this coefficient C appears, which is called a central charge. And this is a very important quantity which characterizes a given conformal field theory. And it will appear in various expressions also later in what I will be discussing. And there is, of course, analogous expressions for T bar, and then one gets also C bar value. In most of what follows, I will just write one set of these expressions because the other ones are completely analogous. So this OP is quite important. This quantity is quite important. And also, it is quite useful and important to look at the modes of energy momentum tensor, which it turns out satisfy some algebra which is called Virasoro algebra. So let me write the expansion of the in the following form. So I may also write ln as the following contour integral. And then similarly for T bar. This time I will still write it. And you may then see what are commutation relations between these modes. So the way to do that, it's similar like yesterday. You can take this definition with contour integral. You write the products which follow from this commutator ln, lm under the integral, and then you play with contours, and you write it in such a way that you have two insertions of t, which you can get them to be close to each other, and then you take the OPE, which is written in the top, so those singular terms, appear, and you compute residues, and then you pick up whatever you have to pick up, and then you find the result. In particular, the C should appear somehow in this calculation. It indeed does. And what you get is the following relation. These ln's and bars turn out to be independent. So this is one reason why you can indeed continue them to, well, think of them as independent algebras. Okay, so this is what is called Virasoro algebra. And you see that it looks like the formation of Witt algebra, which appeared in the first lecture, by this extra term, which is just a constant. Sorry? I don't understand.
So because the C constant appears in the first expression, no, in the upper lecture.
In that OPE?
Yeah.
Yes.
So is there like the commutator hidden somewhere, or maybe in the ordering of the?
No, what I'm not sure I understand, but what I meant is that if you want to compute this commutator or the product ln lm, then you can write it in this way, and then you have T of Z, T of W.
Yeah, but I'm thinking about the first line in that lecture.
This line?
Yeah. Yeah, so I would understand that line.
Well, this is this OPE, right? So you take Z to be close to W. You take product of these operators, and then you see that it behaves like this.
There is again the ordering that is round-written.
Yeah, there is, of course. As I mentioned, I ignore this radial ordering symbol.
Is it related to the commutators of the generators somehow, or?
But which generators? Those.
How to go from the OP of T to the bracket of the mode.
Yeah, so this is what I just tried to explain. I write the modes in this way, right? I can do that. So then in this bracket, I have to compute what is ln times ln minus those in the other order.
Okay, so I mean, then you get the first expression from the calculation. No, the point is that I was a bit confused because we were treating also the T's as operators, and
Yes.
now you were using them as speeds.
Well, T is of course, everything is operator. T is itself the operator, but it has this Z dependence. It's like quantum field.
Yeah, of course.
And ln are just the mode. So ln itself does not depend on Z. This is just the expansion of T. But if ln's are operators, it means that this is an operator in itself. So this is very important to have in mind that this is operator statement, as the name indicates, operator product expansion. This is product of two quantum operators.
Yeah, okay. So when you take the commutators, you kind of cancel all the rest in the OPE somehow.
As I mentioned, I have to compute such a product. So I don't want to give details, but roughly speaking, I can write ln lm in this form. So I get two contour integrals. One with dz, another with, let's say, dw. And I will have here t of z and tw and maybe some other factors. When I have such an expression and I look carefully how these contours behave, then I can take OPE. Well, I can use this expression now. And this is a very good exercise, but thought I wouldn't have that much time to present all details. But now I can use this expression. So instead of this product, I write this thing. And then I just compute these contour integrals, I mean like residues. And I realize that I get that result. So I get something which will still involve some contour integral of t, which will come from this term. And this will look like this L within this is n plus L. And another term will be from this first term. It will be, when I make the integral, just a constant, which is that constant which was c. So this is completely analogous to the way yesterday I derived carefully this result, right? It was the same computation. I mean, the computation in similar spirit. I wrote this as some contour integrals, and well, the computation, sorry, was a bit different. To get this, I knew how phi should transform under conformal transformation, and then I wrote this as a contour integral and adjusted the integrand so that everything was consistent. But it was similar game with the contours. Well, I hope it is more clear. But I encourage everyone to make this exercise carefully. It indeed gives some more idea how everything works. Okay, so some comments regarding this Virasoro algebra for C equal 0. This reduces to weak algebra which is satisfied by generators of conformal transformations into D, which I discussed in the first lecture. And that's one remark. Another remark is that the central charge C does not affect the global conformal group. Which is SL2C.
This class of C equals 0, CFTs has some special properties.
I'm not sure if they have interesting properties. You may call them special, but I think theories with non-zero central charge are, I think, in general more interesting than when say is 0.
You have to get rid of the Weil anomaly.
Sorry?
You have to get rid of the Weil anomaly.
Well, indeed. I mean, depending what you are interested in, what is your considerations. There are some systems where you indeed want to get like total central charge indeed being 0 for that reason. And then you try to cook up various ingredients in such a way that overall you get that. So one might say that it's more interesting, but anyway. When you consider some specific models, it's maybe more easier to discuss some features. Anyway, by this global group, I mean SL2C, and then corresponding algebra is formed just by modes L0, L plus minus 1. So they satisfy more explicitly the following relations, and you see that C does not does not show up here. So global group does not see the central charge. Okay. So this is important object as well. And what I can discuss now, once we have these modes, I can discuss the structure of Hilbert space in this field. So also, somehow in the beginning of the talks, I mentioned that in this quantum theories, we should have vacuum state, which is invariant under global conformal transformations. So I denote it in this way, and I may define it by imposing the conditions that this is annihilated by some subset of those modes Ln for n being greater or equal -1. And then this ensures that the expectation, the following expectation value of the energy momentum tensor, or this remnant of the energy momentum tensor, is 0, which means that indeed this vacuum state is invariant. Under conformal transformations. So for that reason, this characteristic of the state by these modes of energy momentum tensor is important. So this is one state which we, of course, need in what follows. And it is also useful to introduce other states. One particular class of states which I denote in the following way by H bar, and they correspond to primary fields. And this correspondence is referred to as the states fields correspondence. So these are the states, and the fields appear in the definition of the states. Namely, this state is defined in such a way that we take infinite past in a sense, or we take limit when z bar go to the origin, and act with some primary field on the vacuum state. And this H is the dimension or a weight of this primary field. So in other words, you can start with some primary field, evaluate it at the origin, or just consider this limit, and then acting on this vacuum produces you some state, which I denote in this way, and it has quite interesting properties, of course, because it has some nice properties. This is the reason why we use this state. So first of all, these states can be thought of as eigenvalues of L0, which we can also think of the Hamiltonian, because L0 generates dilations, which radial ordering corresponds to ordinary time translations. And I will also not make this computation, but you could do that yourself as an exercise. This is similar like before, some exercise with those contours. So you can write L0 again in the way that I had here as this contour integral. So this is integral of t of z. And then in this state you have this primary field phi. So you can take this limit out of the integral and then compute OPE of t with phi. You remember that in this OPE there arises a term with h. So this term, when you then compute residues, this is the term which survives and just gives this eigenvalue. So you can play a bit with contour integrals to get this result. And then similarly for H bar. And moreover, if you act on this state with Ln with positive n, you get just 0. So you can try to derive these expressions. And I will also introduce the following notation for other states which can be generated from this h bar state by other modes of the energy momentum tensor. These states are important because they arise as the effect of various possible conformal transformations on a given state. Sorry, maybe I write it differently. I'm not specifying here which conformal transformation I'm doing, and for a given conformal transformation, you might need to make some work to find explicitly what you get, but general statement is that what you get would be of the following form. Well, I will ignore for now this barred pieces just for simplicity of notation. And this can be also ordered in some specific way. So, because such states arise as effects of conformal transformations, we need to consider all of them. And all the states generated in this way from a given state with this eigenvalue h form something which is called Verma module. So also all such states are called descendant states. By descendants here I mean all states of the following form. And well, then one remark is that the number of linearly independent states at level n, whereby okay, well, I missed one point. Sorry for that. I should tell you what the level is. So one important statement is that I hope I can squeeze it. You can squeeze it in your notes. You may compute also the result of acting with L0 on such a descendant state. And it turns out that what you get is also, I mean, that this state, this descendant state is also eigenstate of L0, but with eigenvalue which is h, like for this original state, but then plus all these indices n1 and 2 up to the last one. Okay. And where is the color? So this summation is called D-level. So the number of linearly independent states at level n is equal to the number of partitions of n. Well, you can find it from the following generating function. So this number of partitions is denoted often by P of n, and these numbers are given as coefficients in this expression. So I suppose many of you have seen such expression before. So you have original state, there is just one state which corresponds to this one. At level 1 you have just one state which is obtained by acting with L-1 on this state, so this is 1 which is coefficient of this Q. On level 2 you have either the state L-2 or L-1 squared, so we have these two states and so on. Okay, so for some time I will work with these descendant states and discuss their properties. So, well, again, these are these descendant states, but I mentioned there is the state fields correspondence. So, I mentioned what is the field corresponding to this particular state, H bar is just the primary field, but one can also correspond descendant fields corresponding to any of these descendant states. So I'd like to define now such descendant fields. I will denote it in the following way. By, if primary field is denoted by phi, then I will add the following superscript minus n, where in general this n can be a vector. And I simply define them as coefficients in the OPE with energy momentum tensor. So before I just wrote only singular part, but if you would be able to write well, to compute explicitly also this non-singular coefficients that you would, what you would identify would be these descendant fields that I mean here. So that's a definition. And if you recall also the form of the OPE, then from the first two terms, we immediately see that this phi 0 is in fact original primary field, but multiplied by this weight h, and phi minus 1 is derivative, and then the higher ones take some other form. So we will need both primary states and primary fields. Sometimes it is easier to discuss some properties in the language of states. Sometimes it's easier to discuss them in the language of fields. And what is also important that it is quite easy or straightforward to compute correlation functions which involve these descendant fields once you know correlation functions just of primary fields. So this is one of the nice features of those CFTs. Namely, the statement is that the following correlation function can be expressed by acting with some differential operator on the correlation function which does not involve this descendant field. So this is also a statement which follows from conformal invariance, and you see that this conformal invariance gives us, in a sense, automatically many other correlation functions than just those of primary fields. This L minus n is the operator which has the following form. Yes. I mean, yeah, these are primary fields. So what I mean here is that here I insert different primary fields. But on top of that, I include extra field which is not primary, but...
I can exchange descendant field
for
primary and some differential.
Yeah, yes. And this is also one exercise you can make, that this L minus n operator satisfy, well, the Witt algebra, or you can say negative part of Virasoro algebra. So you can think of these operators and some specific representation of negative part of Virasoro algebra. You can just try to make this commutators and see that they also satisfy this relation. So this relations was in essence quite abstract. I didn't tell you what these LNs are, but here we have some explicit realization of them, and it's useful to see that indeed it satisfies those relations. Okay, and another name which is often used and it's important notion is that of conformal family. So in a sense, this is the analog of the Verma module. The Verma module was some subspace of Hilbert space related to a well, formed by all these descendant states, and conformal family is analogous object, but in the language of fields. So the set consisting of a primary field and all its descendants in the sense of descendant fields. And, well, this is often denoted in this way by square bracket with this primary field in a square bracket. And, well, this is important object because, let me say it again or even write that members of conformal family transform just among themselves under conformal transformations. So if you have a given primary field, you can form all these descendant fields, and you can be sure that when you make conformal transformations, you will not go beyond, well, I mean, any member of this family will not create any state which would not belong to this family. And similarly, if you take OPE of T of Z with any member of such a conformal family, you may get only, in the expansion, you may get only members of this family. All right. And finally, it turns out that, in fact, this is possible to write explicit form of OPE to all orders, including well, the terms which are non-singular, and writing their explicit form. And such an OP is important because it enables them to find all correlation functions in a given theory, also those which include those descendant fields. So I will write this OPE well, in a moment. Let me just start with this remark. So again, here the idea is that if you have a theorem where you have this special set of primary fields, and in principle you are interested in correlation functions, multi-point correlation functions also involving other fields, so in particular the descendant fields, and all of them can be deduced from the OPE which I am going to write now for some two primary fields. Let me take them to be located at position z and then 0, just for simplicity of notation, not to introduce another variable. So these are two primary fields. And then one can write this complete form of OPE, which is as follows. So here I have a summation over, first of all, one index P, and then two vectors, which I denote by k minus k bar. In fact, these are vectors, but because of this bar, I don't want to write another arrow. So k is equal k1, k2, let's say up to km, and similarly for k bar. Okay. And here in this OPE, what appears are certain constants. So you may recall the structure constants that we had in 3-point functions. This is almost that, but I need to generalize them a bit. So here I put this k and k bar as extra labels. Then there is some dependence on z. So this combination would be what appears in 3-point function, but then I also have extra power from those components of vector k. And similarly for z bar. And then these descendant fields, this phi p with indices, extra labels minus k bar, which are okay, which can be denoted as follows. So the expression is a bit lengthy, and it takes time to type it, but, well, the message I hope is important, that we can have complete form of this OPE. Okay, and I need still to tell you what it means to have this else acting on the field phi. So, well, this is another piece of notation. It's in a sense analogous to this phi n that I introduced before, but let me, once I type it, let me also type this. It is whatever you get, again, in the OPE of T with some field, any field phi. So if I make OP of T with some phi, then I get some expansion, and the well, there is some functional dependence, this powers of z minus w, but then the operators which appear in this expansion I denote by ln phi, and then I can repeat it many times, not only for primary fields but for all fields, and this is what I mean by this expression, those different L's combined with this field phi. So you see that what I get here is the OPE is expressed through the summation over various other primary fields and all its descendants. And, well, I didn't make the point yet. The point is that you can write explicitly the form of this coefficient C. Or, well, almost explicitly. I mean, there is a way to compute them. Maybe this is a more proper statement. And this is quite a non-trivial fact that this C, I, J, P, K, K bar take the following form. Whereas just C, I, J, P are OPE. Coefficients for primary fields. So, as I tried to advertise in the beginning, that in principle these also so-called structure constants determine the whole theory. And then here are these other factors beta, whose form is fixed by conformal invariance. And they depend only on the corresponding weights, so Hi, Hj, Hp, and central charge C, and of course the Barth quantities. So their form is universal for any CFT. And there is a way to compute them to any order. I mean, for any k, but it is not quite possible to write explicit formula for all k's. But just an example. When this k and k bar are both equal to 1, then this factor takes the following form. So in this way, we know, at least in principle, how to find the complete OP of any of these primary state. And then one can also play with this expression. And in other words, one can also find OP of descendant states. I mean, of all descendant fields. So this is also fixed by the structure constant Cij P. And well, again, let me write it on a blackboard that in this sense, all information about a given CFT is encoded in the structure constant Cijp and weights of primary fields. and one correction here. I have just H, but not H1 and H2. This is still a simple example for H1 being H2 and equal to H, which is in this expression. Okay, so I think this is the moment I should stop. And maybe there is still some question. For those betas, no. You can, they are of course known to higher order, and you can put them to computer and compute as high as possible. But you see, these are complicated functions of H's and C of some kind of random forms.